In multivariable calculus, just as in single variable calculus, as soon as we know how to find the relative maxima and minima of a function, we certainly are interested in finding the absolute maxima and minima of a function, because in that fashion we can solve optimization problems. And very similar to how this has gone in single variable calculus, we will talk a little bit about the theory, but then we'll talk for the most part about some examples. And as I think I had promised at the end of the presentation on planes, when we talked about distances, we will specifically talk about distances in a separate example, because in the end, finding the point that is closest to a certain surface, for example, or that is closest on a certain surface to another point, that is something that actually is an optimization problem. So what do we have? We talk about optimization. We're going to talk about largest and smallest values. It's multivariable because we're talking about functions of several variables, and the optimization is what we will call unconstrained, because for constrained multivariable optimization, that is what we do with Lagrange multipliers, and that will be the next presentation. So we start with a definition that should at least feel familiar, namely a number m is called the absolute maximum of a multivariable function f on a set D, if and only if, well, first of all, there has to be a point P in D so that f of P is equal to m. And second of all, for all other points R in D, we have that f of R is less than or equal than m. So basically, P is an input value, so that the value m that is supposed to be the absolute maximum is assumed by the function, and the value m is then in fact the largest value that the function assumes in that set D. If you're interested in the definition of an absolute minimum, well, that's a number so that there is a q, let's say, so that f of q is equal to that number, and so that for all other points R in D, we have that f of R is greater or equal than that absolute minimum. So that is not too hard to formulate. And if you look at this definition, if we were just for a minute to forget that we're talking about multivariable functions, then this is indeed the definition of the absolute maximum of a single variable function that we have already seen in single variable calculus. So this definition, in fact, is something that could work in any setting where the function may take input values from rather stranger sets than subsets of n-dimensional space. All right, so when we talk about absolute maxima, we want to certainly have some kind of an assurance that we can find those things, and for that we have to dig a little bit into the theory. So first of all, we're going to define what a bounded set is, and a bounded set is a set that is contained in some balls. So basically, if we're looking at this set D here, then we can see that if we find ourselves a center point, we can draw a circle around that center point of a certain radius, and that is then a ball or a disk in this case. And basically any set for which we can do that, any set that is contained in some ball in 3 or higher dimensions, or inside a disk in 2 dimensions, that is what we call a bounded set. Closed sets, on the other hand, closed sets, a good way to describe those is they own their limits. So basically, if we're looking at a set like this one here, where basically the solid line, or the solid curve here says that this part of the curve is also part of the set, and the dotted curve says that this part is not part of the set, then this set D actually would not be closed, and that is because I could find a curve C that approaches this dotted curve here, where everything on the curve is in the set, but the limit of the curve is not in the set, and then that would not be considered closed. So basically, a closed set is something that contains every point that the set approaches. With these two notions, we can formulate the following theorem. If we have a continuous multivariable function that is defined on the closed and bounded set D, then there are points T and B in the set D, so that f of t is the absolute maximum of f on the domain D, and so that f of b is the absolute minimum of f on D. If this theorem sounds familiar to you, it should be, because again, if we are just going to drop the demand that this is a multivariable function, then this is pretty much verbatim the formulation of the corresponding theorem from single variable calculus. The challenge, of course, is that the notions of closed and bounded are something that would require further discussion, and that is typically done in advanced classes that really puzzle the theory behind this theorem apart. What we can also do is we can certainly assure for ourselves that at least the hypotheses are needed. So, for example, if we're looking at the function f of x and y being x squared plus y squared, that is definitely a continuous function on the set D being R2, being the two-dimensional plane. And that set certainly is closed, because if I've got any curve that sits in R2, then the limit of that curve will also be a two-dimensional vector. So that thing is closed. However, the function f has no absolute maximum on D, because of course x squared plus y squared, that grows unbounded as we make x and y large. Similarly, if we're looking at the function f of xy being 1 over x squared plus y squared, that's continuous on a different domain. It's certainly not continuous at the origin, right? Because at the origin we divide by 0 and the function is not defined. However, it is defined on a domain of all xy, so that 0 is smaller than x squared plus y squared, which is then smaller or equal than 1. So that's what people call a pointed disk around the origin. And again, this thing now is bounded. However, f has no absolute maximum on D, because as x and y approach the origin, 1 over x squared plus y squared, of course, gets arbitrarily large. So even though the idea of bounded should be fairly simple to understand, the idea of closed basically means you can't have these kinds of holes that we see in here, and that's what we're going to leave it at for the purposes of a first multivariable calculus course. These two hypotheses really must be satisfied, otherwise this theorem will not work. Okay, we're not going to prove this theorem, because that is something that certainly requires deeper machinery, and that means we are going to start with examples as soon as we remind ourselves of what the process of finding absolute maxima is. Well, what would we need to do? We need to find the critical points, because those could be relative maxima or minima. We need to find the values of the function at those critical points. That way we know which relative extrema are really high or really low. We need to find the largest value on the boundary. And the largest of these numbers is the absolute maximum. So the process of finding these things is exactly the same as for single variable calculus, only that the computations will be more complicated, because for critical points we'll need to work on the gradient, and the boundary, of course, now will be a boundary curve or maybe even a boundary surface, so that will take some longer. One thing that we ought to talk about here is, what's the boundary? We haven't formally defined that, and it's not that hard to do, really. Basically, it's going back to that picture that I showed you when I talked about closed sets. Let's take a look at this set, and it would be very natural to, of course, say that this blue curve here is the boundary. And that would then mean that this point P here visually is on the boundary. And what does that mean? That means I can approach that point from the inside of the set with a curve C1, and from the outside of the set with a curve C2. And if I want to formulate that mathematically cleanly, I would say that if I have a set D in n-dimensional space, actually, again, we're not going to limit ourselves to 2 dimensions, 3 dimensions, or anything like that. These notions are all easily generalized. Then the point P is said to be a point on the boundary of D, if and only if there are vector-valued functions gamma 1, 2 defined on 0, 1. So gamma 1 would be the parametrization of C1, gamma 2 would be the parametrization of C2, and those would have to be so that for all t, gamma 1 of t is in D, that's this one. For all t, gamma 2 of t is not in D, and the limit as we're approaching the point that is not in the domain of the curve for gamma 1 of t, so that would be t going to 0 in this fashion, that is P, and if gamma 2 approaches the left end of its domain, if t approaches 0 for gamma 2, then C2 would also approach the point P. So that means that we can approach any boundary point with curves that are entirely outside and entirely inside the domain, and whether the boundary point then is itself in the set D or not, that depends on whether D is closed or not. Okay, now we can take a look at some examples. So let us find the absolute maximum of the function f of xy being 3x squared plus 2xy minus y squared on a triangle with vertices 0, 0, 1, 1, and negative 1, 1. Well, let's visualize that first. We have an x-axis, we have a y-axis. Here's the origin, 0, 0. Here's the point 1, 1. Here's the point negative 1, 1. And then we are interested in the absolute maximum of this function on this triangle here. Well, that means we first have to figure out if there are any extrema on the inside of the triangle, and then we also have to find out how the function behaves on that boundary. Well, and that shouldn't be too bad, because on the boundary we can just plug in linear parameterizations of line segments. Alright, so first of all, we want to find the relative extrema overall, so we take the gradient of f and set that equal to 0. Well, the partial derivative of f with respect to x is 6x plus 2y, and that needs to be equal to 0. And the partial derivative of f with respect to y is 2x minus 2y, which is supposed to be equal to 0. Well, that tells us very quickly that y is equal to x. And if we plug that into the fact that 0 is supposed to be 6x plus 2y, we end up with, because x is equal to y, we end up with 6x plus 2x, which is 8x, so 8x has to be 0. That tells us that x is supposed to be equal to 0, which then tells us that y is supposed to be equal to 0, and that is the only critical point of the function. Now, just as in single variable calculus, we have to make sure whether this point actually is in the domain, and of course it is in fact on the boundary, so technically we should check that later when we talk about the boundary, but either way, we might as well work it out here. F of 0, 0 is equal to 0, and we would have needed that point for the boundary anyway. Now, if this point had not been inside the domain, just as in single variable calculus, we would have needed to discard that point because it is not relevant for the domain under investigation. It would have been not relevant for the point under investigation. For the boundary curves, well, basically we've got the horizontal line where y is equal to 1. Well, when y is equal to 1 and then x is between negative 1 and 1, we would need to investigate the curve f of x and 1, which will be 3x squared plus 2x minus 1. And that's a curve for which we can just find the extrema with regular single variable calculus. So I take the derivative with respect to x and set that equal to 0. And we end up with, what, 6x plus 2, which gives us x equals negative 1/3. And so that means, because negative 1/3 is between negative 1 and 1, that's a point that we should investigate. And so, because y was supposed to be equal to 1, we need to find out what f of negative 1/3 and 1 is. And that ends up being 3 times 1/9, which is 1/3, plus 2 times negative 1/3 times 1, which is minus 2/3, so we get minus 1/3. Minus 1 is then minus 4/3. And then here, of course, we also have to figure out what f of 1, 1 is. And f of 1, 1 is 3 plus 2 minus 1 is 4. And we have to find out f of negative 1, 1, which is 3 minus 2 minus 1, which is 0. So far, the absolute maximum is 4. And even though the question doesn't ask for it, the absolute minimum actually is negative 4/3. Let's take a look at the other pieces. Y equals x, and then x between 0 and 1, that's the upslope of the triangle on the right side. Well, that would mean that we have to find out what the function f of x and x does, right? Because y is equal to x. Well, that function is 4x squared, and that assumes its minimum at 0, and the origin has been already processed, so we don't have to worry about that. And the maximum is assumed at x equals 1, and 1, 1 has been already processed, so we really have no new information from this part of the triangle. And if we're looking at y equals minus x, and then negative 1 smaller equal x smaller equal 0, that would be the downward sloping side of the triangle in the picture that we had, well, then we have to figure out what f of x and minus x is, and f of x and minus x is, let's see, that would be 3x squared minus 2x squared minus x squared, so that would be 0, and that means we also don't get any new information on that side. And so that means the absolute maximum value is the value f of 1, 1, which is equal to 4. And if we want to visualize that, well, here is the function worked out in MathCAD, and we can see that, first of all, it is certainly defined on a triangular domain, right? In this case, now the y-axis is actually going to the side, because remember that in these 3D pictures, we always have the x-axis going this way and the y-axis going that way. And we can see that the maximum really is assumed at 1, 1. And we can also see, if we want to, that, okay, what did we have? On one of the sloping sides of the triangle, the function looked like 4x squared, that's that part. On the other side, it was horizontal 0, that's this part. And on the third side, we actually had found that there would be an absolute minimum assumed, which we can also see in this picture. So it looks like we have done this problem correctly, and if we wanted to record it for completeness sake, even though it is not asked for in the problem, we could also say that the absolute minimum is the value negative 4/3. Alright, so basically set the gradient equal to 0 and then deal with the boundary, which means we could use this now to actually also solve an optimization problem that we are a bit familiar with still from single variable calculus, and that is that we want to look at a rectangular box without a top that is supposed to have volume 50 cubic inches, and we want to find the dimensions of the box with the smallest surface area. This is a problem that you probably have seen in similar guys in single variable calculus. However, in single variable calculus, we always had to demand that the box had a square base, which actually is reasonable if you want to find the box with the smallest surface area. With multivariable calculus, we're actually going to show not only that it's reasonable, but that it really is the only way to get the smallest surface area. So this time around, we really have a box where we have 3 dimensions, an x depth, a y width, and a z height. And so we're not going to assume that x is equal to y as we used to do in single variable calculus. Well, and now, in order to find the smallest surface area when the volume is given, well, we need to work out the volume equation and the surface area equation. So the volume is x times y times z, sure, width times depth times height, and that's supposed to be 50 cubic inches. And the surface area is a equals xy, that's the area of the bottom, plus 2 times xz, that's this right panel here and this left panel here, plus 2 times yz, and that is the front panel and the area of the back panel, right? Okay, so that gives us an area as a function of 3 variables. Well, in multivariable calculus, we shouldn't be too bothered by that anymore, but since we have an equation that relates the 3 variables to each other, we can eliminate one of them, and I want us to eliminate z, because of course from the volume equation we see that z is equal to 50 cubic inches divided by xy. So that means area of x and y, surface area of x and y, is xy plus 2x times z, which is 50 over xy, plus 2y times 50 over xy. And so that would be xy plus 100 over y plus 100 over x. And that's exactly what we have here. The domain, of course, is that x and y are both supposed to be greater than 0, and the rest is just computation now. So we take our surface area function, and what do we need to do? We need to find the gradient, set it equal to 0. So we set the partial of a with respect to x equal to 0, and that would give us y minus 100 over x squared. When we take the derivative with respect to x, we take the partial with respect to y, set that equal to 0. Well, that gives us a partial derivative being x here, right? The derivative of xy with respect to y is x, and the derivative of 100 over y with respect to y is negative 100 over y squared, and the derivative of 100 over x with respect to y, that's just straight 0, so we get x minus 100 over y squared. That means that x squared y is 100 and y squared x is 100. X squared y is 100, y squared x is 100. And these two equations we just transfer over, and now we have to solve a system of two nonlinear equations in two variables. And as I always say, for nonlinear equations, there is no set algorithms how to solve those. However, when we only have two equations for two variables, typically the best thing to do is solve one equation for one of the variables and plug that into the other equation. So here I think I'll solve for y probably. Yeah, sure. If I solve this first equation for y, I get y equals 100 over, if I solve this, solve for x. Okay, if I solve this second equation for x, I get x equals 100 over y squared. And if I plug that in here for x, I get 100 over y squared. That's the x squared from right up here, and then times y here equals 100, and that's this 100 right here. Alright, so now I have one equation for y, and I'm skipping a couple of steps here again to also simulate the situation that you have when you read an advanced text. People will skip steps. What do I have here? I've got 100 squared on the left side, I've got 100 on the right side. If I cancel 100, I end up with 100 on the left side. And I have y over y to the fourth on the left, which is 1 over y cubed, and I can multiply the y cubed over. So I end up with y cubed equals 100. That's easily solved. That tells me that y is the third root of 100. If I plug that back in here for y squared, I realize that x times 100 to 2/3 is 100. And if I cancel 100 to 2/3, I end up with x equals 100 to the 1/3. And that means that x is the third root of 100 also. And z then, of course, is 50 over x times y, so that would be 50 over the third root of 100 squared. And that would mean, because 50 is, of course, half of 100, I can multiply top and bottom with 2. That gives me 100 on top and a 1/2 out front, and 100 over square root of 100 over 100 over 100 to the 2/3 is 100 to the 1/3, and that is the third root of 100. So this is 1/2 third root of 100. So the only critical point that we can find is that x is equal to y, and they are both equal to the third root of 100, and then z, the corresponding vertical dimension, is 1/2 times the third root of 100. Now we also have to check the boundary here, and basically the boundary is the boundary of the first quadrant. So if my function is a of xy equals xy plus 100 over y plus 100 over x, that function goes to infinity when xy goes to infinity, or when x and y, or one of them, goes to 0. So anytime we approach the boundary of the first quadrant, which would mean, if you want to look at an infinite boundary, that something goes off to infinity, in which case, of course, x times y goes off to infinity, or something approaches one of the axes, in which case x or y goes to 0. In that case, this one or this one would go to infinity. So this is a function that blows up on all sides, and that means that this critical point that we found must be the absolute minimum, and that means the dimensions of this box with the smallest surface area really are third root of 100 in inches times third root of 100 inches times 1/2 third root of 100 in inches. I didn't work out what the decimals for that are, because if you multiply it out like this, you see very easily that the volume really is 50 cubic inches, and you also see really easily that this thing must have a square base, and then this last part here shows that the height is actually half of the width of that square base. Okay, we finish with the computation of distances, and the example that I have here is that I want us to find the shortest distance between the point 0, 1, 2 and the paraboloid z equals x squared plus y squared. If you visualize that, and I would want you to do that yourself, I'm not going to show the picture right now, but if you visualize that, there actually is a way to trick your way through this problem and solve it with single variable calculus. However, I want us to look, and I'm going to tell you how to do that at the end when we do another visualization, but I want us to just realize that distance computations are something for which this kind of optimization is really pretty much made for, because all we need to know in order to find these kinds of distances is the distance formula and the process of finding absolute maxima, or in this case absolute minima. So the distance between a point xy and z of xy on that paraboloid and the point 0, 1, 2, well, that's given by the distance formula. It's the square root of the square of the difference in the x components, so x minus 0 quantity squared, plus the square of the distance in the y components, y minus 1 quantity squared, plus the square of the distance in the z components, z minus 2 quantity squared. And of course, z of xy is x squared plus y squared, so we can plug that in. X minus 0 quantity squared is x squared, y minus 1 squared stays with us, and then we have x squared plus y squared from right here, minus 2 quantity squared. Okay, and so basically to find the shortest distance between this point and this paraboloid, we have to minimize this function. That is why distance computations really ultimately are just done with multivariable calculus, because we can just set up the distance formula and then find the minimum with calculus. The annoying part here is, of course, that we've got this square root. And it turns out that if we were to minimize the squared function, q of xy being x squared plus y minus 1 quantity squared plus x squared plus y squared minus 2 quantity squared, gives the square of the minimum distance. And that is just as well, because then if I want to find the shortest distance, I would just go ahead and take the square root of that. So we're actually going to focus on this function q here. So taking this function q, we need to find where the gradient is 0, so I need to find the partial derivative of q with respect to x. Well, that's 2x from here. The partial of y minus 1 squared with respect to x is 0, and then the partial of x squared plus y squared minus 2 quantity squared with respect to x is 2, x squared plus y squared minus 2 times 2x, and that's supposed to be equal to 0. The partial of q with respect to y, well, the derivative of x squared with respect to y is 0. The derivative of y minus 1 quantity squared is 2y minus 1 when we differentiate with respect to y. And the derivative of x squared plus y squared minus 2 quantity squared is 2 times whatever is inside, x squared plus y squared minus 2 times the derivative of the inside with respect to y, which is 2y. And that's supposed to be equal to 0 also. And so we are again left with a system of two nonlinear equations for two variables. This one is a little bit rougher than the other ones, so let's first just take a look at the first equation. If I cancel a 2 here, I end up with x plus 2 times x squared plus y squared minus 2 times x equals 0. And I can see here, if I factor out an x, I end up with x times 1 plus 2 times x squared plus y squared minus 2 equals 0. And that gives me, on one hand, that x would have to be equal to 0, or that this parenthesis has to be equal to 0, and this parenthesis is basically 2x squared plus 2y squared minus 4 plus 1, so minus 3. So that would mean that 2x squared plus y squared would be equal to 3, and that means that x squared plus y squared equals 3 halves. And what we're going to do now is we're going to solve this system of equations first in the situation when x is equal to 0, and then in the situation when x squared plus y squared is equal to 3 halves. So let's go ahead and solve this thing. I think we are first going to consider the case that x is equal to 0. Well, we have the other equation, which is 2y minus 1 plus 2x squared plus y squared minus 2 times 2y equals 0. And that, of course, with x equals 0 becomes 2y minus 1 plus 2y squared minus 2 times 2y equals 0. We just drop the x squared, right, because we don't have to carry a 0 with us there. We're going to cancel a 2 again. So we get y minus 1 plus y squared minus 2 times 2y equals 0. Alright, and so now if we multiply out the parentheses, what do we get? We get 2y times y squared, which is 2y cubed. We get negative 4y plus y is minus 3y and minus 1. So we get 2y cubed minus 3y minus 1. Now, equations like these are in some ways a trap, because I have seen students use the quadratic formula on something like that, and I'm not happy about it, and I'm not trying to make fun of people, but of course that doesn't work, because this thing is a cubic equation, not a quadratic equation. It's just one of those things where there is a lot of temptation that we should not try to lead ourselves into. So how do you solve the cubic equation? Well, basically, there is the cubic formula, which we don't memorize because it is just a little bit too complicated. You can work it out numerically, so you can use a solver, or sometimes you can use the rational zeros theorem if you're lucky enough that there are certain rational zeros. And this function actually has a zero at y equals -1, because 2 times -1 cubed is -2, minus 3 times -1 would be +3, and then -1, so you get -2 plus 3 minus 1, that is 0. So that means that this polynomial must have a factor y plus 1, and if you then do your synthetic division, you realize that the remaining quadratic is 2y squared minus 2y minus 1. And so again, if you read something like this in a text, well, the least you can do is verify that this really is correct. You realize how people found the factorization, and the fact that it is correct is easily verified by saying that, okay, 2y squared times y is the 2y cubed. Then we have 1 times 2y squared minus 2y times y. That's 2y squared minus 2y squared, so we don't have a y squared term. Then we have 1 times -2y minus 1 times y. That's the minus 3y. And then we have 1 times -1, which is the 1 here. Okay, so that means on one hand we have that y1 equals 1 is a solution, and for the other one now we can use the quadratic formula, and so we get -b, -2 plus minus b squared, 4 minus 4ac, so minus 4 times 2 times -1, which is plus 8 divided by 4. And then if you factor that out, square root of 4 plus 8, square root 12 is 2 times root 3. And if you cancel the 2's, you end up with 1 plus minus root 3 over 2. And those numbers are approximately 1.3660 and -0.3660. So those are the x value 0 and the y value 1, x value 0, y value approximately 1.366, and x value 0, y value approximately -0.336. Those are three candidates for the point where the shortest distance between the point and the paraboloid is realized. And well, we still had the case that x squared plus y squared equals 3/2. Again, we look at this other equation, which was 2y minus 1 plus 2 times x squared plus y squared minus 2 times 2y equals 0. And if we plug x squared plus y squared equals 3/2 in here, we end up with, okay, cancel a 2, right? We have y minus 1. This 2 is also canceled. Then we have x squared plus y squared being 3/2 minus this 2 times 2y. Well, 3/2 minus 2 is 1/2. 1/2 times 2 is 1. So we end up with y minus 1 minus y equals 0. That gives us -1 equals 0, which has no solution. So that means there are no further solutions to this system of two equations in two variables. And well, so now remember that the distance formula is square root x squared plus y minus 1 squared plus x squared plus y squared minus 2 quantity squared, the distance formula for this problem. We can now plug in 0 and -1, and that ends up being a distance of root 5. That's something we can still compute directly, because we get 0, we get -2 squared, which is 4, and we get 1 minus 2 quantity squared, which is 1, so square root of 4 plus 1, which is square root of 5. Square root of 5 is approximately 2.2361. We also have to compute the distance that is realized at x equals 0 and y equals 1 minus root 3 over 2, and that's something that I plug straight into a calculator. The distance ends up being approximately 2.3126, and the distance realized for x equals 0 and y equals 1 plus root 3 over 2, that ends up being 0.3897. So that's just straight computer calculation. I wouldn't want us to do any kinds of acrobatics with square roots and squares for those things. And so that means the last one is the shortest distance, yeah, obviously, because that's the smallest number. And now let's look at a visualization of the whole thing, because it's kind of interesting. that apparently we can have a shortest distance of 2.2361 in some sense, then a further distance 2.3126, and then the shortest distance being 0.3897. And basically, the visualization goes back to what I mentioned earlier on, that this problem actually could be tricked into becoming a one variable problem, and that is because when we are looking at the point 0, 1, 2 and a rotationally symmetric object, and the paraboloid of course is exactly this parabola rotated around the z-axis, right, then it is quite normal to conclude that the x-coordinate of the point where the shortest distance is realized must be 0, because if a point doesn't have x-coordinate 0, then I could make that x-coordinate 0 and get closer to the paraboloid. That's because the geometry is rotationally symmetric. But that would then mean that I would just have to look at the shortest distance between the point y equals 1, z equals 2, and the parabola z equals y squared, which is just a slice of the paraboloid along the y-axis, or the intersection of the paraboloid with the yz plane. And so now let's take a look at this animation one more time as it comes around. Okay, so this is the cross section of the paraboloid with the yz plane. Y goes horizontally, z goes vertically. Here's the point y equals 1, z equals 2, and remember that now x is equal to 0, right? And if you want to see the whole three-dimensional thing in your mind, you would have to imagine that this is rotated around the z-axis to give us a paraboloid. Okay, so the distance, if I now just pick a point on this parabola or paraboloid and let it run along the whole gamut of this parabola, I can compute the distance at every single one of those points. Okay, so let's let it run. And at the first point where the animation stops, I have a distance of 2.236, which is this distance here. And that is locally a shortest distance, because it turns out that if I go a little bit to the left, I get 2.237, and then 2.27, and so on. So if I step a little to the left, I get a larger distance. And if I step a little to the right, come on, oh yeah, that's the pause here. If I step a little to the right, I also get a larger distance. So the geometry is in such a way that this point really here is closest in this area, but not overall, because the distance now is increasing, and the distance is increasing up until the 2.3126 or 2.313 here, because this thing is rounded to 3 digits. So this is now a locally farthest away point, and if I step a little to the left or a little to the right from this point, then I'm actually going to get closer to the blue point again, which, at least when we're stepping to the right, as it's happening right now, is quite obvious. This is a whole lot closer than that, and so this distance now, the 0.39 or 0.3897, that is the closest distance. And because as we go past this point now, we can only go farther away, the shortest distance between the point 1, 2 and the paraboloid really is the approximately 0.3897 that we have in here. Okay, so that does it for this presentation. Basically, what you always want to do is you certainly want to be able to see what's going on, and you want to be able to make sense of the results, just as we also have done here with this cross section. If you find out in the process that maybe there's a way to solve this problem with single variable calculus, great, you can use that as a double check. But in the end, if you've solved the problem with a valid method, then you have the solution, and that is the main thing. And what we have then seen also here in these examples is the power of these computations, because as long as we work through these computations correctly, everything is going to work out just fine. Of course, the drawback is we have to solve nonlinear systems of equations, which is something for which, as you can see here, there is a variety of approaches, and often it's just a matter of pattern recognition, finding a weak spot, finding something that allows you to simplify the equations, or worst case scenario that you just solve for one variable and then plug that into the other ones. That is something that I didn't do for this last example, because solving cubic equations or solving quadratic equations typically leads to uglier expressions than I cared to work with for this example, but that's where that factorization that we saw actually helped us very nicely. Alright, so that means for the homework, really all you have to do is set the gradient equal to 0, check the boundary, move on. Oh yeah, checking the boundary for this example, of course, the boundary would be that x and y goes to infinity, and then the distance goes to infinity, so that was not an issue there. So yeah, set the gradient equal to 0, check the boundary, find the largest or the smallest value depending on whether you're looking for a maximum or a minimum, and hopefully not getting too bothered by the computations in between. Alright, have fun with the homework.